A resounding what's up, CTM students and whoever else may be watching. What's up, what's up? Welcome to 9.2. We're talking about polygons today, and lots of terminology here. Most of it hopefully you're familiar with. If you are a CTM student at least, you should know what these things are. If you're new to geometry though, this will be a good overview of quite a few things that you see in geometry here. These are all terms we should know by the end of this lesson. I won't necessarily talk about every single one of these things, but most of them we will touch on in the context of these notes. Well, let's get rolling. Let's get started here on this part. I'm going to draw some examples of things that are polygons, and in this side I'm going to draw some examples of things that aren't polygons. We're not going to formally define what polygon means here, but I think by just looking at these examples you'll be able to tell what it does mean. And so polygons, I will verbally at least define what it is. They have all straight sides, that look a little neater, all straight sides, and they all connect, and there's no overlapping. So here's some examples of polygons. Not drawn perfectly. Imagine these are connecting right at the endpoints. So if I want to be more precise there, I should get rid of those little extra parts. That wouldn't be a polygon if it actually extended farther. They have to connect right at their endpoints. And so here's a pentagon. Here's a triangle. Here you can have the parts kind of caving in. We would call that concave polygons. This part, or this one, I could draw something like this. This would still be a polygon. That's connected there. Still a polygon. Still all straight sides, and they're all connected right at the endpoints. Here's another one, four-sided. Here's some that aren't polygons though. So even though this is all connected, there's no open parts, it's a circle, you cannot have curved parts in a polygon. So no curved parts are allowed. This kind of hourglass type shape, that wouldn't work either. You got some curved parts there. If you had something like this, but there was an opening or a gap in between, that's not going to work, so I purposely left a gap there. An angle itself, not a polygon because it's not three or more sides. You have to have that as well. And then this would not be a polygon because you have segments that are overlapping each other. So this portion by itself could be a polygon. This portion by itself could be one, but altogether it can't be one. It has to be just one region of space enclosed. And another non-polygon example, a line like that. So hopefully you have a good idea of the difference between polygons and things that aren't polygons from there. Here we have some special names that you're going to need to remember. So special polygon names. These are ones you should know by heart. They actually have names. If you go on something like Wikipedia, you can look up all the crazy names they have for all the different kinds of polygons, going up to like a million-gon, a megagon. Megagon is a million-gon. Yep, megagon. Literally, megagon. I'm not joking. Alright, 3, 4, 5, 6, 7, 8, 9, 10. We're going to skip 11. That's not one you need to know by heart, but 12 is, 20 is, and then just in general, and what do we call that? So 3, hopefully we know that's a triangle. 4 is a quadrilateral. And then after that, they all have the suffix gon at the end. So it's a pentagon from here, pentagon, a hexagon. This one seems to trip people up. Heptagon, if you think of the heptathlon in the Olympics, that's a 7-event seven events in one that the women do, instead of what the men do. We'll get to that in just a second. The men do 10 events in 2 days. The women do 7 events in 2 days. Some of the world's best athletes doing the heptathlon, and the starts with a D. It's a decathlon. So I'm going to get there. I'm trying to do 2 things at once here, though. A nonagon for 9, a decagon for 10. If you think decade, that's another really good way to remember. Decagon is 10. Decade is 10 years. Nonagon, nine and non kind of sound the same. Octagon, if you think of MMA, if you're a mixed martial arts fan, they fight in the octagon. There's 8 sides to that thing. Hexagon, I kind of think of beehives, but I don't have a clever way to remember that. The Pentagon, think of the building in Washington, D.C. This one is a dodecagon for 12. Dodecagon is 12. And I think of decagon being 10, and then I just added 2 more letters to that. That's a good way to remember. It's 12. 20. I don't have a clever way to remember this one yet. Icosagon. And then in general, n sides, we can just call it an n-gon. So if you had 11 sides, if you had 13, 14, 15, if you had 28, if you had 76, you would just say, for the purposes of our class here, a 76-gon or a 13-gon, something like that. But if you have one of these particular numbers of sides, you should tell me the specific name that you see here. So make sure you got those down. And then a summary. A lot of what we're doing here in this chapter is just a summary of things you learn about in geometry. If you take a geometry course or have taken one, we know we go a lot more in depth in those classes. This is kind of like the surface stuff, or the main things to know from geometry. So here it's the sum of the interior and exterior angle measures. I'm running out of space here. Angle measures. And so these two in particular are going to be in any polygon. Let's put that in our different color. So these two are going to be for any polygon, and then these two will be for regular polygons. Regular polygons are polygons that have all equal sides and all equal angles, equiangular and equilateral. So in regular polygons here, I'm going to underline regular, underline any. That is vital to know the difference there. So any polygon. So if I look back to here, I could say this one might be a regular polygon. If all these sides were the same and all the angles were, then it would be. But the rest of these would not be regular polygons. You don't have equal sides and equal angles. Let's see, we got that back in black here. The sum here of the interior, I'm going to abbreviate INT for interior. Interior angles, remember that's a symbol for angle, and this is just meaning angles if we put an S after that. This one I'm going to have the sum of the exterior angles. So I'm saying all of the angles put together in any polygon. Do you remember an equation like this? This, just listen for right now over here, and just, I'm going to put it in green. Don't actually write this stuff down. This is just to listen to right now. So how many degrees in a triangle, a single triangle? That's 180. How many in a quadrilateral? Maybe you remember that as 360, maybe not, but where does that come from? And then how about a pentagon? And how about a hexagon? And so on and so forth. How do we know what each one has? Well, how many triangles can you split this up into? 2. That's not a very good triangle. Let's make that a little better. That's better. This would be 180, and this would be 180. So put together, that would be 360. For a pentagon, you can make 3 triangles like that. 180, 180, 180. Put it all together, and you've got 540. Same thing here. With hexagons, you're going to have 4 triangles. You put that all together, and you get 720 degrees. So what's the pattern? Well, it looks like it's 180 times 2 less than the number of sides. Another way to say that is n minus 2. Subtract 2 from the number of sides it has and multiply that by 180. The sum of the exterior angles is always just this. It's always 360. Let's see, I lost my train of thought a little bit there. I had somebody knock at the door and I had to go answer that, but let's see where we're at. We're at this 180 degrees and 360 degrees, and then down here each interior angle and each exterior angle. Let's see what we have for that. So if this is in any polygon, you have this and you have this. If we're finding the measure of each interior angle in a regular polygon, so think of it, again, let's not write this down or put this off to the side here, but if I drew a regular pentagon as best as I can freehand, these are all the same then, and all these angles are the same here, 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 and here, and they're all adding up to 540, which comes from 5 minus 2 times 180. Whew, about to sneeze, there it is. So 540 divided by, what are we going to divide by? If each one has to be the same, if it's a regular polygon, we would take 540 and divide it by the number of sides there are, divided by 5. So in general, it's just what you had for the total and divide that by how many sides there are. That's going to give you each one. So we just take this, n minus 2 times 180, and we divide it by how many sides there are, n. That will give us our degree measure. So let's make a little note of this. This comes from here. And then 360 for each exterior angle. Each exterior angle is, we're talking about exterior angles like this one. This one, what would be the measure of that particular degree measure, or that particular angle right there. If they're all adding up to 360 and you have 5 of those exterior angles, this one, they all have to be the same since it's regular. It's the same idea. You still divide by how many sides there are, and that's going to be the number of exterior angles, is that n number, and then 360 is the total. So the total divided by how many there are gives you the measure of each one more time. And so let's do the same thing here. That comes from here. Right, so moving on. Here is the actual Pentagon building in Washington, D.C. Picture of that. And it is a regular polygon. All these sides are the same. But let's do one now where we have a regular polygon. And ooh, I just gave it away back here. But that's fine. We'll make sure we got this one down. So we should know what it is already based on what we did back there, but yeah, that is fine. We'll just see it twice. Reiteration is good to an extent. I don't want to hear the same thing 263 times, but I don't mind hearing the same thing twice to make sure that it really gets in there, really sinks in. So determine the sum of the measures of the interior and exterior angles. I'm starting to write the same thing twice. I don't want to write the same thing twice. There we go. And exterior angles and the measure. So we're going to determine the sum first and the measure of each interior and exterior angle in a regular pentagon. So if it's regular, we know they are all going to be the same angles for the interior and exterior angles. They all have to have the same measurement. So we can go back to this. Yes, I know we talked about this already, but let's write it down more formally here. So we're going to be using these formulas and just putting those into practice. So first of all, sum of the interior angles. Let's do that first. The sum of the interior. Let's draw a picture to go along with this as well. Actually, I will move this over here then and draw your best regular pentagon. I'm going to cheat, so I have a really nice looking one here. I'm going to use this little tool, but you draw this as best you can freehand. I'm trying to make my sides the same as best I can. And we are going to be talking about some exterior angles here too. So this one would be the exterior angle. Let's label that in red right here. This is an exterior angle. And then this one on the inside, that's going to be an interior angle. So what is the sum of the interior angles? We're just doing the n minus 2 times 180. So we have 5 minus 2, not times 2, but minus 2 times 180. That would be 3 times 180, which would equal 540 degrees. And if we wanted to find what each interior angle was, we would take that value and divide it by 5. That's my n minus 2 times 180 part on the top. Divide it by how many sides there are. And here you've got your answer. 108 degrees would be the measure of each interior angle. So let's write that in now in our different color that we know it. That's 108 degrees right there. We're trying to find the measure of this one. And let's also write this down. We know that n equals 5. And so because it's a pentagon, we know it has 5 sides. We've got that right there. Now what about the sum of the exterior angles? What are they going to add up to? Well, that from our formula table here, it's always 360. It doesn't matter what kind of polygon it is. It doesn't matter how many sides it has. The measurement is always 360 degrees. It is independent of the value of n. It doesn't matter what n is. But now each exterior angle, the measure of each one, we take the total and divide it by how many there would be. There would be 5 of these exterior angles, just like we talked about and saw here on this one. So we're taking 360 divided by 5. That leaves me with 72. Another way to think of that, though, that would work, since this is 108, all these have to be the same. Let's put that here. I meant to put that in here. Since it's regular, we can put all equal angles and all equal sides here. So let's make those marks. They all have the same number of arc marks. Those are all congruent. The same number of tick marks is what I call those. Those are all congruent as well. And so now this angle measure right here would be, if I think of this as 108, which it is, these are all the same, I can also think of it as 180, the whole line, minus 108 would leave me with 72. That's another way to get the measure right there. But either way, you get that as your answer. Now, moving on to talking about triangles a little bit more in depth. And we're going to classify triangles. So the classification of triangles, what does that look like? There's a couple different ways we can classify triangles, by either their angles or by their sides. By angles or by sides. By angles, we can say either acute, obtuse, or right. So let's talk about that here. We'll just freehand these pictures. Acute, make sure each angle that you're drawing is less than 90. They all have to be acute angles. So you can't have any right angles, you can't have any obtuse angles. So here, these are all acute angles. Let's put that in our different colors. So all acute angles for an acute triangle. Now if it's obtuse, you can't have all obtuse angles because triangles add up to 180. If you got something that's bigger than 90, the other two added together would have to be less than 90 themselves. So the other two would have to be acute, but one, and only one, ends up being obtuse. So here's an example. These are just the examples of these types of triangles, but this one has one obtuse angle. And a right triangle is just going to have one right angle. Again, the other two would have to add up, instead of be less than 90, would have to add up to 90 if you had one of them being 90 to start. So here, let's say that one's my right angle. This one, these two would have to be 90 to add to that one to get 180 for the whole thing. For the sides classification, we have something called isosceles. Got an E in there, sorry. So we got an extra E there. Equilateral and scalene. Isosceles triangles, some books will tell you that it's at least 2 congruent sides. Others will tell you that it is exactly 2 congruent sides. our book says exactly 2, so that's what I'm going to go with and tell you it's exactly 2 congruent sides. And it also ends up being that this is true as well, that the angles will end up being, these base angles is what we call those base angles will end up being congruent also. But this has 2 congruent sides. We're going to say exactly 2 instead of at least 2 for our book here. Equilateral has exactly 3, all 3. So equilateral, trying to draw all the sides, all the angles, so that they are the same. So this, and this are all the same. This angle, this angle, this angle are all the same. And this one has 3 congruent sides. And then Scalene finally doesn't have any congruent sides, so they're all different. Here's one where they're all different lengths. So here we have no congruent sides. And generally in geometry, just a quick side note here, you can't trust the way a picture looks. You have to trust the measurements that are in the picture. If you are given tick marks or angle markings that say they're congruent, then you can also assume that that is true. And then one more thing before I move on to example 2, we'll squeeze this in here. Similar polygons are, I feel like this one's important enough to define. Similar polygons to define formally in a written out manner here. Polygons where, if I write CORR, that is shorthand for corresponding, where corresponding angles, so angles that match up, in other words, have equal measures and where, so the measures are the same of the angles and the sides are proportional. So where corresponding sides are proportional. So from there, let's do example 2. The triangles depicted, we're going to draw some triangles below. The triangles depicted below are similar. What we need to do is set up a valid proportion and then solve for x. And I'm going to use my straight line tool on this one just to make a really nice drawing. This is not drawn to scale, however. You can't say in geometry that the drawing is necessarily to scale unless you are told that it is. And I'm going to tell you right now, this one is not necessarily drawn to scale. So you can't take a ruler and measure this and try to figure it out that way. Basically, that's what that means. So let's say you got that, and let's say we have one right here. Trying to draw it so that this is parallel to this. And then from there, I'm going to label some parts. I'm going to say that this is 15 right here. This is 20. This part from here to here is x. And generally, in geometry, wherever you put the number or the letter to represent a length, if it's right in the center of that, that's what we're assuming is the length. We're assuming the length from here to here is 20, and from here to here is x. Sometimes they'll use things like this and draw lines there as well. But if it's in the middle of a certain segment, just assume that that's the length of that particular segment. And so what is our solution for this? First setting up the proportion and then solving for x. So similar parts, they're proportional. Match up the sides. So match up the parts of the small triangle that you see right here to the larger triangle outlined right here. So what's the part here that would match up with the part here? Well, clearly I think that's 5 and 15. These things are going to match up, and so let's put that like that, and 5 and 15. So 5 to 15 would match up with, this is small triangle on top to the big triangle measurement on the bottom. The small triangle measurement here would be x, But then what's this one? Is it 20? Well, 20, no, because 20 just goes from here to here. This is the tricky part about this problem. The whole thing is what we need to measure. The whole length of this triangle here matches up with the whole length right here. So from here to here is going to be similar, proportional from there to there. So we would have to say x plus 20. And so let's make a little note here in our different color where these came from or what we're doing. These are coming from the small triangle, and these ones are coming from the big triangle. These are the parts that match up. 5 matches up to 15, x matches up to x plus 20 in these two triangles. From there, now we can cross multiply. So let's draw a little x there to represent that, cross multiply that. We've got 5 times x plus 20 would equal 15 times x, 15x in other words. Distribute the 5 through. Let's show the steps here in the color. We got 5x plus 100 equals 15x. And now we're getting close. Subtract 5x from both sides. That'll cancel. You're left with 100x, or 100 equals 10x. Sorry, just 100, not 100x. We're dividing both parts by 10 there. And that 10 will cancel with that 10. 100 divided by 10 gets us our answer that x equals 10. And if we plug that back into the picture, it should make sense. If this is 10 and that's 5, this would make the whole thing 30 to 15. And 10 and 5, that's 2 times bigger. 30 to 15, that's 2 times bigger. They seem to match up. They seem to work well. We could also plug 10 back in up here. 10 over this would be 30. Does that equal 5 over 15? Sure does. They both would reduce down to 1 over 3 in the end. You could also use a different valid proportion setup. You could say that 5 over x, so this part compared to this part, would equal 15 over 20 plus x. Or you could flip-flop these, and that would still be okay. So there's different ways to write valid proportions, but you just have to compare the matching up parts to each other in a proper way. Example 3 now. Example 3. We're going to have some quadrilaterals that are similar. The quadrilaterals depicted below are congruent now instead of similar. So depicted below are congruent. That means exactly the same size and shape. And determine the following. Now I'm going to draw a quadrilateral looking kind of like this. You draw this as best you can on your paper. Trying to make it a trapezoid looking shape. I'm going to go like that. And I'm going to make a copy of this. I'm going to put it over here. I'm going to rotate it around, and also I'm going to flip it. So don't draw, you can draw this one, but don't draw this one quite yet. There we go, mirror that, delete that one. So it's congruent, they're all matching up, and there we go. So let's call this, let's go with T, R, A, and P. And then over here, this will be Z, O, I, and D. So I kind of spelled trapezoid, but I left out the E. And let's say this one here is 20. And this one over here is 10. I'm also going to tell you that this angle is right and this one's right. Same thing here and here. So I'm saying they are congruent. If you had to determine a congruence statement, what would that look like? Congruence statement, you have to make sure the letters orders match up. The order of the letters has to match up correctly. So you could say, you could start off with T, R, A, and P. For triangles, generally we would write a little triangle symbol in front of it. For quadrilaterals, sometimes you write a four-sided kind of square looking shape. Sometimes you won't see that though. We're just going to leave it without that. So if I put those letters in that order, T to R to A to P, and I say it's congruent to something, can I just say Z to O to I to D? Does it match up in the same order? Does T actually match up with Z? If you look here, no, it doesn't. A matches up with Z here, and R matches up with D here. Looks like P matches up with O, and T actually matches up with I. And so I have to say from there, based on what I just said there, that T matches up with I. That's clear, so I'm going to put T here first and I here first. If I have R next, T goes to R in the same way that I goes to D. It's the longest part of the trapezoid. So this would be D, and then from here let's go to A, so R to A, that's D to Z. And then let's just make sure that that matches up. A to P, is that the same here as it is there? Yep, it is. So this is Z to O. So the congruent statement looks like that. And let's just make a little note of that the letters, they must match up in order. If you just wrote trap and zoid and you didn't actually check that the T matched up with the Z, which it doesn't, then you would not have the right congruent statement. And getting this part right makes everything else we're going to do here easier if we got that part right. So the letters must match in order. They have to match up. I'll say they have to match up in order. So let's check out part B now. Let's say we're trying to find the length of AR and also the length of ID. So I've got a couple things here. I know that TR is 20, and since TR matches up with ID, I can say that those things have to be congruent. This would have to match up with this over here. And so I'm going to circle this. The stuff in black here is original, but then the stuff in red is stuff that I can prove based on the things being congruent. I can also say similarly that since that's 10 right here, that would be 10 right here. So I'll connect those two, and that tells me my answers here. AR would equal 10, and ID would equal 20. And you'll notice something here. I didn't say length of AR, and this is something that you're allowed to do. You just write the letters right next to each other with no symbols above it. That refers to a distance. So let's make a little note of that off to the side here. So no markings above the letters. A lot of this, if you've taken geometry, hopefully is coming back to you as we're going over it. No markings above the letters refers to a length or a distance. If you have the markings, then you're talking the actual pictures themselves, like a segment. You're talking a line, a ray, but no markings means the distance from that point to that point. Part C, what if I asked you to find the measure of angle O? There was one other thing I wanted to add in here. I wanted to say originally in black here that this was 52 degrees. And so how could I find the measure of that particular angle right there? I would say the measure of angle O. This would have to be, remember trapezoids, it's a special type of quadrilateral. It's got 4 sides. This would have to add up to 360. We can split that into 2 triangles. We can also think of 4 minus 2 times 180. So 360, they all add up to 360. We can do 360 minus the 3 that I know. That will give me the one that I don't. So I do 360 minus 90 plus 90 plus 52. That's 360 minus 232. And could I say 360 minus each one of these separately? Sure, that'd be fine as well. But this, either way you scramble those eggs, you get 128 degrees right there. So this one would get filled in right there. This is 128 degrees right there. And how about part D? If I said the measure of angle T, what would you say? T, it looks like that's matching up with I right here. And so T and I should be. Okay. I just noticed, I was like, earlier in the notes, I had flipped these letters around, and so I had different things matching up with different things than what I originally had, but this is fine. The way I've done things is also correct. So I've got 52 matching up with the 52 over here. This angle I, this angle T match up. You'll notice also, look at the congruent statement. Since we did that correctly, T is the first letter, I is the first letter. They have to match up. They have to have the same angle measurements there and there. R would have to be the same as D, A with Z, and P with O. So measure of angle T, either way you look at it, 52 degrees right there. And it matches, let's make a final note there, this is matching, matches with measure of angle D. And then just one more thing I want to talk about in this lesson that gets covered is quadrilaterals. The book describes it a little differently here, or it doesn't put it quite in the same format, but I think the way we'll do this here, we'll give everything the book had plus one little extra thing that I think is really valuable to know. And so let's start off by drawing any old quadrilateral. Nothing special about it. I don't want to make that even look parallel, so I'm gonna do that instead. So no parallel parts necessarily, no congruent parts, nothing like that. And this is quadrilateral. So let's put that, let's write it in our different color. This is a quadrilateral. As I move down from there, I could have three different things happening. I could have one pair of parallel sides, two pairs of parallel sides, or no pairs of parallel sides. And a special type that can happen with no pairs is a kite. So it doesn't mean that I would have to have, just because it doesn't have a pair of parallel sides doesn't mean it has to be a kite. It could just be just a plain old quadrilateral, but it could be a kite. It could be a special type of quadrilateral. As I move down here, I'm going to get more and more specialized. So right there is a kite. I could have a parallelogram, something like this, where you have two pairs of parallel sides, which I can denote like this. And the markings that I'm putting on here is what it has to be at the very least. Or it's the definition, that's a better way to put it. It's what defines a parallelogram is that you have two pairs of parallel sides. What defines a kite is that you have two pairs of consecutive congruent sides. There's other properties that hold true about these things. We can prove things about parallelograms like opposite sides are congruent, opposite angles are congruent, consecutive angles add to 180. There's a bunch of different things we can say that is true or that are true about these shapes, but this is the definition of what you have for these shapes. So the definition, what you see here, is just the definition. And a trapezoid, that just has one pair of parallel sides. And so this would be a trapezoid here. From there, as we move down, why don't we do this stuff in a different color? So I'm saying this branches off or splits off into that, these three things. And then from there, you can split off of the parallelogram into two different things, two more specialized types of parallelograms. From the trapezoid, there's a special type of trapezoid as well. And so from here, you could have something that looks like this, where all the sides are congruent, or you could have something like this. Notice these are both special types. They're specialized types of parallelograms. Opposite sides are still parallel, but here I'm saying that all sides are also congruent, and here I'm saying all angles are also congruent. What's this called? This one's a rectangle. That's the one more people remember. This one, though, is called a rhombus, not necessarily a square. I didn't say these were all 90 degrees, but I did say all the sides were the same. And then a trapezoid, you could also have, branching off of that, you could have the legs being the same length here and here. So it's still a trapezoid, still have parallel sides there and there, but this is an isosceles trapezoid. Just like an isosceles triangle had two congruent sides. Same thing. I just wrote triangle. An isosceles trapezoid has two opposite, or has two congruent parts as well. And so one more thing to branch off of. These two can come together, the rhombus and the rectangle can come together and form a super quadrilateral known as a square. The square has the properties of both. It's both all 90 degrees and all congruent sides. A final note that I want you to make off to the side here, I've talked about this as we've gone through this, but it's this, that all quadrilaterals here, they have the properties of the things above them. So a square is both a special type of rectangle and rhombus, but it's also a special type of parallelogram since that's connected to it above it, and it's a special type of quadrilateral. However, it's not connected directly to the things above it to a kite. You'd have to kind of flow up and then flow back down. We're talking just flowing up. And so, is it a special type of kite? No, it doesn't have the same properties that a kite does. We can't have a kite that has, excuse me, we can't have a square isn't a special type of kite because we have two pairs of consecutive congruent sides, but they're different. They're all different. The square here is all the same. So let's write that down. As you go up, as you move up, it has all the properties of things connected to it directly above it, but you can't flow in a different direction from there. So all quadrilaterals here have the properties, all the properties of the ones connected above it. And for example, we talked about a square. Let's refer back to that. A square is a special type of rhombus, rectangle, parallelogram, and quadrilateral. As you move up, you see all those things connected to it directly above it. And so that will do it for our synopsis of polygons for this lesson. Hopefully you remembered a lot of these things if you had taken a geometry course before. If this is brand new stuff to you, hopefully what you're seeing here made sense, and it'll be a good foundation that has been laid for you in your geometry class as you continue forth from this point. So as CTM students, make sure you go back and know all these things. I think I talked about almost all of them, but if there's something here you don't recognize, you don't understand what it means, go back to your vocab and check those things out in your book. Hopefully have a good day, and I will probably see you later, or at least you'll hear me later. I probably won't see you later necessarily unless you're one of my students, but you'll hear me. Okay? Have a good day. Catch you later. I'll stop talking now.